Hey guys, welcome. Yeah, so our second example on how to use power series to solve a given differential equation. And so if you haven't, I encourage you to watch example 1 because I'm not going to repeat some of the details that I mentioned in that example. But yeah, the equation we have to solve this time is right here. And this is a power series centered at x equals a, but what we're seeking is a power series centered at x equals 0, so a Maclaurin series. So our solution y is going to look like this. And term by term writing of our solution, we'll have it look like that. And so y prime is this, and y prime in closed form is this, and this is y double prime. And now that we've got y double prime, y prime, and y, we could rewrite our given equation using series, and so that'll look like this. Now notice that y prime is being multiplied by this x here, which is highlighted right there. So to make progress on where we're at right now, which is right here, we need to multiply in this x, meaning this x to the n minus 1 is just going to be x to the n. So it's going to change from n minus 1 to just n, the exponent of x here. But even after doing that, you'll see that we have other things to fix. In particular, this here starts at n equals 2. This will be at n equals 1, and this is at n equals 0. So to fix that, first, you need to push this sigma forward so it starts at n equals 0. I showed you how to do that in example 1. So if you need to, watch example 1. But what you have to do to get this sigma to start at n equals 0 is change this n minus 1 to n plus 1, this n here to an n plus 2, this a sub n to a sub n plus 2, and this x to the n minus 2 to just an x to the n. If you do all that, then you could change this from n equals 2 to n equals 0. Okay, cool. Now, after doing all that, right, remember, you've multiplied this x in, and you've changed this to start at n equals 0. So after doing all that, you're almost good, only that this sigma starts at n equals 0, this sigma starts at n equals 1, and this starts at n equals 0. So what you'll have to finally do to fix that, so to fix everything, is, well, evaluate this at n equals 0, and evaluate this at n equals 0. So in other words, take the n equals 0 term from here and from here and set them aside, meaning write them in front, and then what you have left can be written with a single sigma starting at n equals 1. So, doing everything I just said, you can write this, is what I'm saying. Okay, it's a bunch of steps all together, but you get it. You multiply that x in, you change the sigma so it starts at n equals 0, and then you take the n equals 0 term from here and here, and those two are right here. The a0 is from n equaling 0 in this part, and the 2a2 is from n equaling 0 in this part, and then you have all three sigmas starting at n equals 1, and so that's everything here. Yeah? Okay, cool. Now, we need this here, this whole thing to equal 0. In order for this whole thing to equal 0, we need the sum of these two guys to equal 0, and we need what's multiplying x to the n inside of sigma, so all of this. We need all of this to equal 0. So we need two things to happen. We need the sum of these two to equal 0, and we need all this stuff right here, multiplying x to the n inside sigma to equal 0. So this is what we need. And now we need some space. I'll remind you of what I had just displayed, which is like this last guy, right? That's where we left off. But yeah, so let's make room and go back to that. All right. So this is what we said. Yeah? Okay, cool. Now, as we did in example 1, we're going to use this here to solve for a sub n plus 2. And you actually get a nice little relationship between a sub n plus 2 and a sub n if you solve this here for a sub n plus 2. And it's pretty easy algebra, like just do it carefully. But yeah, what I'm saying is this here is equivalent to this here. Now, if we let n equal 0, you will see that this here, which is equivalent to this here, for n equals 0, this here actually is the same thing as that. In other words, this guy here is redundant to this. It's just this when n equals 0. So basically you can ignore this here because the information in here is contained in here. Yeah? Okay, cool. That's when n equals 0, you get a sub 2 is equal to negative a sub 0 divided by 2, which is what this tells you, which, you know, from here. Anyway, let's move on. So n equals 1, and we're evaluating for different n's because while this is like a nice relationship between the coefficients of our solution y, like it's not terribly helpful. So we need like to kind of establish the pattern of the coefficients, and that's why we're like evaluating different values of n. Okay, cool. Next is n equals 2, right? And I almost had like a typo here. I wrote minus a sub 0 here, but it's plus, right? And obviously this is just a sub 0 divided by 8, but I chose to write the denominator in this cumbersome way so that you could see the pattern of the denominators on the even coefficients of our solution y. Okay, cool. And our odd coefficients, well, you haven't seen enough, but let's display another one and talk about what's happening in the denominator of our odd coefficients of our solution y. So here we just have 3, and now we have 3 times 5. So guess what's going to happen when we look at a sub 7? We're going to get in the denominator 3 times 5 times 7. So basically the denominators of all the odd coefficients of our solution y are going to be the product of all the odd numbers starting from 3 all the way up to this odd number, whatever it may be. So like if we write the odd coefficients as a sub 2n plus 1, their denominator is going to be like 1, I skipped 1, but you could go 1 times 3 times 5 times all the way to 2n plus 1. Yeah, okay. If we write, yeah, okay, you get it. So here's what we're saying. All the even coefficients a sub 2n will be of the form negative 1 to the n, or will equal negative 1 to the n times a sub 0 divided by 2 to the n times n factorial, which is perhaps easy to gather looking at this guy and this guy, right? And then what I was just saying about the odd ones is that a sub 2n plus 1 will be negative 1 to the n times a sub 1 divided by the product of all the odd numbers starting from 1, or if you want, starting from 3, all the way up to the 2k plus first odd number, right? So whatever number this number is right here, the subscript of a, right? Okay, cool. And so then now finally we write our solution y as this here, and that's because we factored out a sub 0 from all the even ones, and we can write all the even ones once we factor out a sub 0 in closed form like that, and once we factor out a sub 1 from all the odd ones, and by even ones and odd ones I mean all the even powered x terms and all the odd powered x terms, and yeah, anyway, you get it. And so this is our solution here, and an example when we're able to recognize our final solution in series as a Maclaurin series, right? Like once we wrote it in this form, we were able to recognize the Maclaurin series this and that. But here, we're not able to do that with this guy here, and that's sometimes the case when you're using power series to solve differential equations. But yeah, notice that this guy though here, in the first part of our solution, we can recognize. Think about the Maclaurin series for e to the x. So if you modify that to be the Maclaurin series for e to the negative x divided by 2, you'd get this here. So our solution starts with y equals a sub 0, or some constant alpha, times e to the negative x divided by 2 plus this other weird yeah, right? Okay, function. Okay, cool. All right. That's it for me, and keep watching. Example 3 will wrap this up nicely, and look out for that. Take care.